waves can be spread out over many atoms. The basic premise associated with molecular orbital theory is that if two atomic orbitals can overlap with one another from two different atoms, this will result in two different types of molecular orbitals. In one case, there would be a bonding type or a constructive type of interaction, which would tend to draw two nuclei closer together. But then there are also anti-bonding combinations, which are destructive combinations that then would potentially cancel some of the bonding kinds of interactions. Depending upon how many electrons are available for the forming these bonds, this can result in an attraction or possibly no attraction between these two atoms. As a relatively simple example of the types of interactions that might occur in molecular orbital theory, let's consider the constructive and destructive interference that can occur when two hydrogen atoms come together to form molecular orbitals. If we have two hydrogen atoms that have s orbitals happen to have the same phase, and we bring those two atoms together, much like in valence bond theory, we can have a constructive kind of interference, and this then results in an increase in the electron wave between the atoms, and this then results in a bonding type interaction. We refer to this as the bonding molecular orbital. If we then have a situation where the two atoms have different s orbitals with different phase, so one would be, say, positively phased, and in other words, similar to the crest of a wave, and the other 1s atomic orbital on a second atom is got a negative phase associated with it, then when we bring these two atoms together and look at the resulting wave, we would have a destructive interference between the two atoms, and the wave itself would have no or limited electron density between the two atoms, as shown here in the bottom. This then is a consequence of bringing two atomic orbitals together to form two molecular orbitals. The top orbital would be the bonding combination, and the bottom combination would be the so-called anti-bonding molecular orbital. Another way to think of this is in terms of an energy diagram. So again, if we bring together our two atomic orbitals, we can get a bonding combination, and this bonding combination is due to a constructive interference, and the energy of this combination becomes stabilized or becomes lower in total energy, whereas the anti-bonding combination is not as energetically favorable, and it is pushed to higher energy. So in this case, then two atomic orbitals then results in the formation of two molecular orbitals, one of bonding character and the second of anti-bonding character. There happens to be a node present in the anti-bonding combination. The symbolism associated with this bonding combination, the anti-bonding combination, is shown here. The sigma type orbital is shown by the Greek letter lowercase sigma. The bonding combination is lower in energy than the anti-bonding combination, which is given the symbol of sigma star. But in essence, the then the question is, how many electrons do we have available to put into this energy diagram? And so since both hydrogen atoms have one electron, we have a total of 2 electrons total to put into our molecular orbitals. We would start out by putting those 2 electrons into the lowest energy orbitals first, and so they come together and are both placed in the sigma bonding orbital and are spin paired. This then results in the formation of a single bond between the 2 atoms. So in this particular case, if we were to draw out a so-called orbital diagram, there would be 2 orbitals, the first being labeled sigma, the second one being labeled sigma star. The one to the left is a little bit lower energy, and it's the one that contains the 2 electrons that are spin paired. In terms of a similar kind of electron configuration, we would write this in terms of sigma and then represent the 2 electrons as a number superscripted and to the right of that symbol. Similar to what we had discussed previously from our Lewis dot structures and the valence bond theory, we can talk about the so-called bond order associated with molecular orbital interactions. And so the general formula associated with determining bond order for 2 atoms involved in forming molecular orbitals is given here. So in essence, the bond order is determined as half of the number of electrons that are in bonding type MOs, subtract away the number of electrons that are in anti-bonding molecular orbitals. So in the case of there being a pair of electrons in both being in a bonding type orbital, we would say that that is a single bond. And if we had 2 pairs of electrons in bonding type orbitals, that could be a double bond, and we could have up to triple bonds. These are typically associated with both sigma and pi type orbitals. We can also have bond orders that have fractional bond orders, so it is possible to have a bond order of 1/2, but these tend to be less stable and sometimes energetically not stable enough to be observed at room temperature. So, in terms of our hydrogen molecule, the question is, what is the bond order in H2? From Lewis dot structure, we predict a single bond, and indeed the bond order that one would calculate using molecular orbital theory would be 1/2 times the 2 electrons that are in the bonding type orbital. There are no electrons in the anti-bonding type orbital, so we end up with a single bond. This slide summarizes the rules associated with molecular orbital theory. So the first rule is that if you have some number of atomic orbitals for a particular molecule, you have to have an equal number of molecular orbitals. Generally, there will be the same number of bonding molecular orbitals as there are anti-bonding orbitals, with the total equaling the number of atomic orbitals that you started with. Also then, atomic orbitals combine to form molecular orbitals when they have similar energies, and again, you're going to end up with one combination that is stabilized, the bonding combination, and another combination that is somewhat destabilized, the anti-bonding. Overlap increases. The more overlap that you get, the more energetically stabilized the bonding combination becomes. So this causes a greater decrease in the energy. So that is likewise associated with how destabilized the antibonding combination is. And then each molecular orbital can have no more than 2 electrons, and generally it obeys the Pauli exclusion principle, so that those 2 electrons have to have opposite spins in order to be in the same molecular orbital. And then in some cases, if orbitals, molecular orbitals occur at the same energy, we refer to these as degenerate orbitals. And so these orbitals can, if they have electrons in them, we're going to put electrons in following Hund's rules, such that we first end up with 1 electron in each of the degenerate orbitals before we go and do any kind of spin pairing. This slide is attempting to try to explain what happens when a photon of energy interacts with a molecule. In this case, we have the dihydrogen molecule, and there are 2 electrons in the sigma bonding type orbital. If we have a photon of the correct amount of energy that can promote an electron up to the sigma star orbital, that would then give you a situation where we have a 1 electron in a bonding type orbital and 1 electron in an anti-bonding type orbital. And this produces a situation that is known as the excited state for H2. This particular excited state has a bond order that is essentially no net bond, or a 0 bond order, because we have an equal number of electrons in bonding and anti-bonding type orbitals. The out-of-phase combination of the atomic orbitals essentially cancels the bonding in the constructive addition combination, and that then causes a weakening of the bond, and in essence, in this excited state, the 2 hydrogen atoms break apart into individual hydrogen atoms. So you see here both the orbital diagram and the electron configuration based upon the molecular orbital designations. To further demonstrate the effect of having electrons in the anti-bonding orbital, let's consider the molecular orbital diagram for bringing together 2 helium atoms. You might first balk a little bit at this because, of course, helium has a completed valence shell and does not need to form a bond to become stabilized. So, if you were to bring together 2 helium atoms where electrons are in the 1s orbitals, you would again get a bonding combination and an anti-bonding combination. But in this particular case, we have the possibility of not only putting just 2 electrons into the bonding orbitals, but we have an additional 2 electrons that would go into the anti-bonding orbitals. This then would result in a bond order of 0. We would have the situation where there really is no molecular orbital bonding in this type of combination. So you have an orbital diagram where the number of electrons in bonding orbitals and anti-bonding orbitals are equal, and therefore the anti-bonding orbitals cancel the bonding orbitals. So in this slide, we can calculate our bond order for the hypothetical dihelium molecule. We have our molecular orbital energy diagram as shown here, and so the question, what is that bond order? So here's our equation for calculating the bond order. It's 1/2 of the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So in our case, it's 1/2 times 2 minus 2, which 2 minus 2 is 0, so we have a net 0 bond order in this particular molecule. which is perfectly consistent with what we would have expected for a noble gas trying to form any kind of bond